Okay, so ready to go, David? Okay, so last time I was consulting my notes, physical memory. I was talking about B0 mapping, and I didn't talk about shimming. I'll talk about that next time. I'll talk a little bit about shimming, but today we want to talk about diffusion weighted imaging. And so what I'll do is I'll talk more about the theory of how the images get that way and how you analyze them, but not really about any practical pulse sequences. And then next time I'll talk more about what are the actual pulse sequences that we use for this. So diffusion. So diffusion it's a microscopic process where individual molecules are sort of bouncing into each other like little hard ball bearings at a very high rate. They're moving around. At some of them are going 100 miles an hour in that tiny little space before they hit something. And the end result is that in real life it's a 3D thing. So if you put a particle right at the origin, and then it's all sort of bouncing around, and it sort of goes someplace. Now it'll tend to sort of, on average, if you look at all the places it went to, on average, it's going to be, if you're just having a process that has sort of a uniform chemical structure to it, your average is going to be 0, right there. And every once in a while, a particle might, end up sort of getting kind of far away, but that's pretty rare. So if you look at a population of particles, basically what you end up with is a Gaussian. So if you look at all their different positions over time, most of them will be sort of close to the middle, and then most of them, and a smaller number, will have sort of gone far away. And you'll end up with a Gaussian distribution of particle positions. But it's dependent on time. So if you do this in 1D, what you get if you start off. So if you start off with the particle right at the middle, or with all the particles right at the middle, you can sort of imagine that you have like a delta function right at the middle. So pretty much everybody's right at the middle. And then what happens, the longer you diffuse, so if you diffuse for a small amount of time, what will happen is you'll end up with kind of a little spiky Gaussian. And then over time, the Gaussian will sort of get less tall and sort of more spread out like that over time. And so you can describe that Gaussian, or just kind of the average position after some amount of diffusion, you can describe that in one dimension as the square root of 2 times the diffusion constant. So different substances will allow different rates of diffusion, depends on how viscous they are, and then the total amount of time. So basically that the width of that distribution will get bigger over time, and it will get bigger depending on whether or not you have the diffusion constant of whatever situation you're talking about is bigger, because particles will go faster. Maybe there's less of them. And then there's 2 in there for 2 dimensions. The same thing at the same thing in 3 dimensions. Like, you know, if this is, you know, a 3-dimensional position vector, the same thing in 3 dimensions is just 6 dt. So this is 3D. So in real life, it is 3D. So that so this was worked out, you know, in the 19th century. I'm not deriving any of the equations, but you can just look at the final result, and it sort of makes sense. You know, if it's longer, it's going to be wider. If the diffusion constant is faster, it's going to be wider. And an example of the diffusion constant in the brain, that constant, you know, for example, brain D, you know, equals something like 0.001 millimeters squared per second. That's the units of that constant. So what are we talking about here in practice for these distances? They're going to be on the order of a couple microns, a couple thousandths of a millimeter. So this is a physical process of the atoms just bouncing into each other and moving a small distance. Now we're going to try to measure it somehow. And so it turns out that since we can get a signal from these atoms, the MRI signal, we can actually use the MRI signal to actually measure this. And so how does this work? And first of all, remember, like in real life, here's a voxel. You know, what's in a voxel? Well, you know, there's some neurons, there's some, you know, blood vessels, maybe there's some axons running this way, and some axons running that way. You know, it's an unholy mess. And so what we're doing, we're always talking about the, you'll see we'll talk about the apparent diffusion constant. So it means, like, what does the diffusion look like, assuming the whole thing was uniform? Of course, it's not. But we're sort of approximating, you know, what directions the molecules are going to typically move at a length scale of, you know, 10 microns, 1 to 10 microns. So that's, you know, 1,000th to maybe 100th of a millimeter. So it's a very small, it's a microscopic measurement, sort of similar to T2. Same with T2 and T1. Those are microscopic measurements as well. So how do we measure it? So it's a very straightforward plan, which is we just use the gradients as usual. So how does diffusion weighting work? Well, the basic idea is very straightforward. So the basic idea is, let's just do it. Let's talk about diffusion in the x gradient direction. So here's the BZ field in the x direction. Okay, so remember, it's everything's about the BZ field because that's the thing that controls the precession. So but we're talking about the x gradient, so the x gradient causes a linear change in the z component as you move in the x direction. So if you turn a gradient on like that, so there we turn a gradient on. So what's going to happen to the individual spins? So let's just look at, you know, one of the individual spins sort of sitting, you know, right here. So it's possible that the spin might, say, diffuse in this direction, or maybe it went in that direction, or, you know, maybe it went in, you know, into the board, or maybe it sort of came out of the board, or maybe it went this way in the x direction. So it could have gone in any of those directions and anything in between. So diffusion's always happening. So the way we get diffusion weighting is we first turn on a gradient. Now, what does the gradient do to the spins? We know exactly what the gradient does to the spins. It dephases them. It sort of messes up their phase, gets them out of phase with each other. And so what's going to happen is if we turn the gradient on, we're going to really kill our signal. So turning a gradient on is like a T2 star thing. It's a static magnetic field offset, and the effect is it's going to cause the spins to get out of phase. So that's kind of a bad thing, you would think. But the basic way that diffusion works is turn the gradient on for a period of time in one direction, and then wait. So let's define some numbers. So this, in diffusion, the amount of time the gradient is on is often called either sort of small delta t, or just small delta. If you read in the literature, they usually use that Greek letter for that. And now we turn it on in the opposite direction. And so this is the same time, same amount of time here. That's that same delta t. But then we need another number, which is kind of the spacing between these gradients. So that's usually that one is called a capital T. And then last but not least, we need how high the gradient is on. So here's the strength of the gradient. So that's gx here in this case. Okay, so those are the three numbers that affect diffusion. So now we turn it on the opposite direction. So what happened was we turned it on. It messed up the spins, and then we waited a while, and even more diffusion occurred. And then we turned it on the other way, exactly for the same amount of time, and the same strength. So this is that same gx over here. That's the same number. So what happens? Well, it will just make everything right again. So it will essentially, whatever damage it did to the phase when the gradient was on over here will now be fixed, except if the spin moved. So if the spin moves, then it won't be fixed. So, but there's different directions it could move. So if the spin moves, say, in this direction, coming out at you, it will end up in the same position in the gradient, because this strength of the gradient at that point in x. So remember, this is x, and this is actual space we're talking about. So if it just moves sort of in this direction, in and out, and stays in the same x position, nothing will happen. And so that one will get fixed perfectly. What if it moves in the y direction? So if it moves in the y direction, it's also going to be in the same position in the x direction. And so that one will also get fixed. It will only get damaged and not fixed properly. This gradient won't fix things properly if it moves in the x direction. Now we can't tell whether it moved kind of in the negative x direction or the positive x direction, because that would have the same effect. So if it moved like a certain distance in the negative x direction, the gradient is going to fix it a little bit, but not too much. But if you went the exact opposite direction, it's going to fix it exactly the same amount. And so we can't distinguish like which direction the diffusion we can only distinguish the axis of diffusion. We can't distinguish the actual direction, like, say, minus x or x. So that's the fundamental way that you actually measure it. And the way you measure it, the end result is, if diffusion in axis of gradient, less signal. So you get attenuation. So we're measuring this not by a positive signal, but by a negative signal. So if diffusion occurred in the x direction, then you're going to get less signal. Now, of course, it's not going to go in the x or the y or the z direction. It's going to go in some other arbitrary direction. But what happens is the signal you'll get will just be whatever direction you went projected onto the x-axis. So, if this is the x-axis, and say you went in the direction of the y-axis and also the x-axis, then you just take the projection, the amount of movement you went in the x direction. So that's what so you can see that's kind of an ambiguous signal, because if I went this way, I would get the same x projection as if I went that way, because that would be the same amount of x projection. So that's fundamentally how you get a diffusion weighted signal. But clearly that's not going to be enough to solve the problem. So let's just talk briefly about, this isn't the practical sequence, but just to sort of build out a whole sequence so we can see how this would work. So if we were doing it on a slice basis, maybe we would do a slice select. So here's the RF pulse. So we do an RF pulse, and here's the slice select. And then we do these diffusion gradients, and we could do them on different axes, but let's just say we do it on the y-axis. So here it is on the y-axis. So we put a big gradient on, and then we wait a while, and then we put the exact same thing on. So this is, you can sort of think of this as the preparation. So we haven't recorded any data yet. We're just sort of preparing. So this guy is, prep. And then this guy is, make image. So now we have to make an image out of it, because we still have to, do all our gradients. And so now after we've done that preparation, then we've got to do, say, some phase encode, and then here's our readout. We got to do the readout business and make an image. So this is not practical. We'll say, and then we would get, our echo would occur over here. So here's sig. There would be an echo over here that, we would ignore. I mean, the FID we ignore, and then here's, put it on the gradient line. So here's the FID we ignore, and then there'll be an echo over here that we're recording. So not practical, but just gives you some idea. We'll talk about like spin echo and other not practical. But it would be somewhat diffusion weighted. Now, one thing you'll see with this, what about this? Doesn't that do diffusion weighting? It does. So here's another example where just about anything we do causes a whole bunch of different kinds of weighting. So here the slice select turned out to, first we turned the gradient on this direction, and then we went and did the exact same amount of time in the opposite direction. That's going to cause some diffusion weighting, because it's the same thing as this. What about this? That's going to cause some diffusion weighting, because we turned the gradient on in one direction, and then we turned on the other direction for the same amount of time or the same amount of area. And so that's going to cause, unfortunately, some diffusion weighting too. This won't cause any diffusion weighting particularly, But if, say, we do a rewinder, that could potentially cause some diffusion weighting. So it's all over the place. So why do we say we can have a diffusion weighted scan? Well, the idea is we just do a really biggie. So diffusion, to get a good diffusion weighted signal that sort of dominates over the other signals, like T2 weighting, basically we just do a very large gradient. And the longer we wait between when we do the opposite versions of it, the stronger the signal will get, because there's going to be more time for diffusion to occur to sort of go to a different part of the gradient so that it won't get fixed properly by the opposite lobe. So what is the way that we actually measure it in practice? And so the way we measure it in practice is for a particular, so the amount of attenuation we get for a particular diffusion a diffusion constant. So here's that's kind of what we're trying to measure. We're trying to measure like how much diffusion occurs. Was it a lot, and was it in the x direction, or was it a small amount, mostly in the y direction? So the way that we measure this is the way that we measure the attenuation. So this guy is the attenuation. So that means like the lessening of the signal. We have to measure the attenuation somehow, and so we're going to have to measure something without the diffusion gradients on. So the way that this is measured in practice is we take the signal, so it's a complex valued signal, which is our reconstructed image, and this means like just take the amplitude of it, and this is the signal with the diffusion gradient on, and we just take the ratio of that to the signal with the diffusion gradient off. So that's the signal with the diffusion gradient off. So that ratio, that so the attenuation just equals like this. So this is diff grad off. And then this is, diff grad on in some direction. So obviously it's going to be different for different directions. In some direction, we didn't say what direction, but in some specific direction. So and what is that equal to? So that's equal to, so basically just it's a very simple equation. It's got minus b times d. So that's our first equation. So it's just an exponential decay. So whenever e to the minus something, it's basically just something that starts at 1 and falls off. So if you make a bigger b, it's going to fall off quicker, because you remember that's just like T2 fall off. If the number after the minus sign is bigger, that's a faster fall off. So if this b, we haven't said what b is yet, but if this b is bigger, it's going to fall off. And that b has something to do with the gradients, how big the gradients are. And then if the diffusion is faster, so if it diffuses out further, then the signal is going to fall off further, because it's going to get further away from where it was supposed to be to get fixed by the opposite gradient. So that's a very simple equation. So we just have now b. So what is b? So b is just a measure. So you've probably, if you've ever done any diffusion weighted imaging, you probably know about B. You've probably heard of a B value. So what is a B value? What's the definition of a B value? So this is attenuation. And this guy is grad on. So it's basically just a way of, there's various different ways of defining it, but one popular one is it just combines all these three things, because all these three things increase the diffusion weighting. So if you make a stronger gradient, that's going to mess up the phases more, and when you fix them, if you were in a different place, you'll have a more attenuation. If you wait longer, there's going to be more chance for diffusion. That will cause more attenuation. If that's T. If you make the gradient on for longer, that's going to cause more attenuation. So all those things are in there, and so the equation for B is the gyromagnetic ratio times the gradient squared times how long the gradient was on squared times the time that the gradient was on minus the time between the two lobes of the gradient minus the time each gradient was on divided by 3. So whatever, we're not going to derive that, but that's just, it's basically just an equation that says, it just goes, this guy goes in here. You can just stick it into the exponent, but it's it's cleaner to look at it this way, because in some respects it doesn't matter, because all of these things can be traded off for each other. So if you make the gradient, if you leave the gradient on longer, that's equivalent to turning the gradient strength up, and that's equivalent to, that's more effective than just turning the time up, because the time is not squared. But whatever, they all affect the strength of this. So it's a single number that sort of tells you how much diffusion weighting this particular opposite gradient setup is going to give you. And then we plug that into this equation, and then we collect two data sets, and then we can solve for D and sort of figure out what what the apparent diffusion coefficient is. But now we've got all the problem of all the different directions. So let's just consider a case. So here's XY axis. Now say diffusion actually was, there's a lot of diffusion in this direction. We can't tell which way it was, whether it was going that way or going that way. We can't tell that, but we just know along that axis there was a lot of diffusion. And what about this axis? So that's a different axis. There's a lot of diffusion. And so what our diffusion measurement does is it measures the projection. It measures the projection onto the x-axis. That's the same as that. But you'll notice that it's exactly the same in those cases. So if we measure this distance, or this distance, or this distance, we can't tell those apart. So we just get one measurement, and the one measurement just says such and such amount of diffusion occurred in the x-axis. And so from that measurement, we actually can't tell, whether it's this or that, or maybe it could even have not gone. It could have just been like that. That would have given you the same number. So it's quite an ambiguous number. So it turns out, if you want to actually just figure out what is the strongest direction of diffusion, you need more than just 3 numbers. So you would think you would need at least 3 numbers, because you have x, y, and z axis. But it turns out you need 6 numbers in order to disambiguate these situations. And you can sort of see how ambiguous your signal is, because you've got each signal in the x and y and z axis can't tell sort of which direction it's going. And so because of that, you can sort of think of it, because of that, you're going to need more numbers. And so you actually need a tensor. And so we need minimum of 6 measurements to find one principal axis of diffusion. So, and that's it's actually a matrix of 9 numbers, but it's a symmetric matrix, so there's only 6 unique numbers in it. So that's a tensor. And so we won't go over the whole. So a tensor, you can sort of think of a tensor as like, normally at an XYZ point you have one number, like say, the density, or how much T2, what's the T2 value of that point. So a tensor in 3D will sort of splay that out into 9 numbers. And you could sort of imagine, a tensor is kind of looking at the neighbors. It's a derivative kind of thing. So it's looking at the neighbors in various different directions and sort of splaying out a measurement at one point into kind of an infinitesimal measurement that has 9 numbers instead of just 1. So because that's kind of what we're trying to do. We're trying to make a measurement like, which way is it going? Is it going slightly that way, or slightly that way, or slightly up, slightly down? So now we have to draw out the diffusion tensor. So the diffusion tensor is used for an equation that will just generate D, which is that's just this D right here. That's just a scalar. That's just a single number. But we're going to define this single number, sort of classical diffusion coefficient, as a matrix of numbers. So here is the actual measurement direction. So this guy is a measurement direction. So that's a vector that tells you what direction you measured. Now you might wonder, how do you measure some other direction than X, Y, and Z? Well, that's very straightforward. If you want to measure, say, a direction that's halfway in between, say we wanted to measure this direction, so here's the X, Y, and Z axis. What if we wanted to measure a direction that was like that? That was, in between the X and the Y axis. So a direction like that is going to be measured just by turning on 2 gradients. So if you turn on 2 gradients, what will happen is they'll just add to each other everywhere and effectively rotate the gradient. So turning on the X and the Y gradient at the same time will make a uniform change in the gradient moving, along an axis in between the X and the Y gradient. We talked about that before, so you can sort of think of similar to like, so if you want to put on diagonal stripes, you just turn on the X and the Y gradient at the same time, and that will effectively give you diagonal spin stripes because it effectively rotates the gradient direction. It doesn't it doesn't just sort of add to it, it actually rotates it. So that's the gradient, that's the measurement direction defined by, so that's just a vector, a 3-dimensional vector that says what direction did you measure in, and you can measure anywhere around 360 degrees, but since we can't tell, minus from positive, you only have to measure a hemisphere. So we measure a hemisphere, and then we've got the diffusion tensor, and so the diffusion tensor, here's the dy, y, dz, z, so it's got 9 numbers in it, in the tensor, and here's d, x, y, and d, the same as dzx, and then there's dzy and dyz dyx. So this is a symmetric matrix. So here's the diagonal of the matrix down this way, but then these guys are the same. So xy is the same as yx, and these guys are the same, and these guys are the same. So there's only six unique numbers in the diffusion tensor. So this is the diffusion tensor. And then that's multiplied by the direction again. So the direction's kind of squared here. U, I, U, Z. So that thing, so if we write this out sort of more simply, what it says is, D number equals, U vector times D matrix times U vector. But this vector, normally when we write out a vector, we think of a vector as a column vector. So here's a column vector, matrix multiplying a column vector. This guy, to turn that into a row vector, we have to transpose that guy. So that's what the T, there's different symbols for transpose, but the T means sort of like, turn rows into columns. So how do we get a number out of that? Well, if you look at this is, when we talked about sort of matrices, if you take a matrix and multiply it a vector with it, it rotates and stretches the vector, and the output of this is a vector. So this guy is a vector. And then when we multiply it by this guy, since this guy is transposed, ux will be multiplying by ux, or whatever you get after doing this operation, and then uy will be multiplied by this guy. So you'll get, that's a dot product, so you get a number. So now you can sort of directly see how all these numbers get squished into a single number, the diffusion coefficient. So there's like 9 plus 3 is 12 plus 3 is, so 15 numbers all multiplied by each other, and you get 1. So how do you actually measure this? Well, you've got to make multiple measurements. So we need so basically this is known. This is measurement direction again. So those are known because we're setting the gradients in such a way. And so we have 6 numbers to solve for. So that means we need a minimum of, of 6, non-redundant directions. So if you measure in the x direction, we can measure in the x, y, and z direction, and then we could measure and say, halfway between the x and the y direction, halfway between the x and the z direction, halfway between the y and the x direction, something like that. So we need 6 non-redundant measurements. Of this kind, where we, turn the diffusion on in a particular direction, and then divide it by the image brightness that we get without the diffusion gradients on. So we need six measurements of these guys. We only have to measure the brightness of the image with the gradients off once. So typically what you do, we'll separately do this measurement and then do 6 different diffusion. Oh, sorry. Man, how could I have done that? S, signal 0. Okay, grads off diffusion gradient on, sorry. Okay, so we do this, we measure the gradients off just once, and then we do 6 separate images with different diffusion gradients, and then we'll have enough numbers to be able to sort of insert them into this tensor. And that will basically tell us, in the XYZ coordinate system, which way the diffusion is going. But the problem with it, you might notice there's a problem. It's all in terms of X, Y, and Z. What if the diffusion is in some other axis? And so that requires that we solve the eigenvalue problem. And so what is that? So the eigenvalue problem is we take that matrix, and so what we want to do is we want to figure out we need to get the principal components of that matrix to figure out what the direction, so this is just measuring diffusion in an XYZ coordinate, but what if the biggest direction of diffusion is halfway in between the X and the Y coordinate? That we're not going to be able to figure that out from this matrix directly. And so for that, we have to solve the eigenvalue problem. And so the eigenvalue problem is to figure out the eigenvectors. And so here's an eigenvector. One of the eigenvectors, what did I use? In my notes, we'll just call that, there's 3 of them. So what this equation says is, this is some vector, it's an unknown vector, and when we take this diffusion tensor and operate it on that unknown vector, the result is it just causes it to shrink or grow. It doesn't cause it to rotate. And so this guy is a scalar, and then we're multiplying that by the eigenvector again. So this is called the eigenvalue problem. This is kind of the way that you get principal components. So this is, this guy is an eigenvector. It's an unknown. There's 3 of them. So this guy's an unknown. So we try to figure out what random orientation vector that when we operate this matrix on it only grows, or shrinks or grows. So the idea is that if you find one that has a large eigenvalue, so this guy is the eigenvalue. So this guy here, so this guy's the eigenvector. So the eigenvector is just a direction, but the eigenvalue is how much of a growth do you have. And so when you solve this problem, what you do is you get a series of eigenvectors and corresponding eigenvalues, and they tell you in order. The first eigenvector tells you, with the largest eigenvalue, tells you which direction is the biggest. And then the next one tells you what direction perpendicular to that first one is the second biggest. And then the third one tells you what direction perpendicular to both of those is the third biggest. And so after you've solved this, what you end up with is, like what I call, the technical word for it is a pill. So you end up with a little 3-dimensional pill. So here's the surface of the pill like that. And so you can sort of think of it as here's the surface coming out at you. It's like a little 3-dimensional pill. It's got 3, that's what the eigenvalue problem gives you. And what it gives you is the first eigenvector. So this is the, epsilon 1. That first eigenvector is going to give you, with eigenvalue 1. So the eigenvalue will say how long it is. The eigenvector just says which direction it is. So that's going to give you the direction in which the diffusion is the greatest. So this is eigenvector with eigenvalue 1, largest. So that's the first eigenvalue. So that tells you, like, that's the direction, that's the long axis of the pill. And then there's going to be, and it's an ellipsoid. So it's an ellipsoid. So you could, a very simple ellipsoid would be one in which the diffusion was the same in all directions. That would be a sphere. So a sphere is a kind of an ellipsoid. But in the general case, it's gonna have 3 different axes. And so there's one axis, and then there's going to be a second axis perpendicular to that one that will be the second most extended axis, and then there'll be a third one which will come out at you, which will be perpendicular to these other 2. And that's the smallest axis of the little pill. Okay, so we're not quite done. We're almost done yet. So what do you typically do with this? Well, one thing you can do with this, so once you've done all this, so you collected all your data, you got your tensor, which was in the XYZ, and then you did the eigenvalue problem on it to figure out, like, what is the direction of the 3 perpendicular directions. So all you're doing is you can think of this as just finding another coordinate system. XYZ is just an arbitrary coordinate system relative to the brane. What we want to do is find the real coordinate system. It's another orthogonal coordinate system, so all the axes, the XYZ axis of these eigenvectors are perpendicular to each other. It's just we rotate the coordinate system until we find one that sort of like fits the pill. That's what solving the eigenvalue problem does. But now we want to actually use it, and so typically the kind of things that you would use it for would be to look at the eigenvalues and sort of make some other simple equations with them. And so one would be the apparent diffusion constant. So it's apparent because there's a whole bunch of junk in there, and we're just sort of approximating it with just a uniform thing. So the apparent diffusion constant it's sometimes called the mean diffusivity. So that's the same thing, and it's basically just the 3. It's just kind of the average of the 3 eigenvalues. So these numbers, divided by 3. So those numbers can, either be big or small, because, it could be a really diffusible part of the brane or not a diffusible part of the brane. And then there's, these are the diffusions in the 3 principal directions after we found this rotated coordinate system. So that's the mean diffusivity. So that just says, it doesn't tell you how anisotropic it is. It just says that's the average diffusivity when you go across all the directions. And then the other thing that you often might measure would be the fractional anisotropy. So this is mean diffusivity. This is, apparent diffusion coefficient. This is, fractional anisotropy. So this guy goes from 0 to 1. So the fractional anisotropy. So this one is just there's several ways of defining it, but you can either sort of define it in terms of the mean diffusivity, but that's a little more complicated. You can just sort of see how this works. So you just subtract all these guys from each other and square them to get rid of the sign. plus x2 lambda 2 minus lambda 3 squared plus lambda 1 minus lambda 3. So you basically sort of compare them all to each other, square them, add them up, and then divide them by 2 times each of them squared, plus lambda 2 squared plus lambda 3 squared. And so the end result you get, end result is something that goes from 0 to 1. And it'll be 1 if it's really diffusing in one direction and not another. And it will be 0 if it's basically, you can work it out if these guys are all the same, then this is going to work out to 0, which would be like uniform diffusion. Okay, so we finally covered all the main equations, but so this, what we're talking about here is Gaussian diffusion. So we're just assuming that everything is describable by a little pill, by a little ellipsoid, a little Gaussian ellipsoid. But what if it's not? So what if it's, so the only thing we're allowing basically is for the diffusion to be different in different directions, but it still has to be Gaussian. So this little pill is kind of a Gaussian pill. It's still, so if you go in one direction, it's still a Gaussian pill like that. And it's a Gaussian pill in the other, it's a Gaussian pill in, the second principal axis and the third principal axis. But what if it's not like that? So in that case, we might need a diffusion surface because we have non-Gaussian diffusion. And so what's non-Gaussian diffusion? Well, you could easily have a situation where you've basically got a situation, let's just do it in 2D. So say you've got a situation where there's a bunch of fibers going this way, and then there's a bunch of fibers that are crossing them, say going this way. So say there's a lot of fibers going this way, and then there's less going this way. So if we do all these measurements, what's going to happen is we're going to end up with fitting this with this ellipsoid, this pill. And so say we measured the diffusion in a bunch of different directions, like say 60 directions. So we measure the diffusion in this direction, we got a big number, and then we measured in that direction, smaller number, this direction, very small number, and then we get a somewhat bigger number over here, which we can't tell apart from that guy, and then we can't tell these guys apart from each other. So say we measured in, say, like 60 or 100 directions. What we would end up with is something that didn't look like a pill. It would kind of look like a cross. It's going to come out like this, and then it's going to go like that, down here like that, and then symmetrically. So it's a symmetrical thing. It's going to look something like that. So that's a diffusion surface that we made a whole bunch of measurements of this surface by measuring it in all different directions, because we know that we actually have non-Gaussian diffusion. So what happens if we try to fit a pill to that? Well, we're gonna mess up. We'll get a pill that looks like this. It's gonna be somewhere in between. So that would be our Gaussian approximation. And the Gaussian approximation is going to be wrong. It's going to be like halfway in between the two main directions of diffusion. So that's why you might want to measure more directions or a diffusion surface. So, more than 6 directions, for example, 128. So you might have to measure like 64 or 128 just to pick up 2 different diffusions, real diffusions. So if you had like crossing fibers, which happens all the time in the brain, like sometimes the axons go this way and then there's some other ones that are going almost perpendicular to them. That's very common. If that happens, you're going to have to, 6 measurements is not going to cut it, because the 6 measurements is only going to allow you to approximate this with a pill, with an ellipsoid. So you might have to make 64 or 128 directions just to distinguish 2 real directions of diffusion. So that's typically the kind of thing you might want to do if you're going to do some kind of track tracing. And I'll talk a little bit about that next time. So track tracing, where you're trying to sort of essentially do diffusion imaging, get these little diffusion surfaces all over the place. And here's another diffusion surface, and then what you're trying to do is figure out which way are the fibers actually going, like what's connected up to what. So I'll end there, and it's a brutal full 60 minutes, David, and then I'll take some questions. Okay, guys, sorry, that was